So I'm giving a talk on modeling complex systems in Python with Gaphor. My name is Dan Yaw. I've been kind of facilitating the Michigan Python meetup for the last few months, which has been fun. And I also work at Ford as an engineer, and we do systems engineering of complex systems. And over the last 3 years, I've been working on an open source Python modeling tool, because I've seen that we have all these great enterprise tools that are very complex and take a long time to load, and maybe sometimes they're a little slow to get new features and stuff. And I thought it'd be great to have an open source tool that any engineer can learn on and apply these kind of model-based systems engineering techniques. And in the talk, I'll go through what those are. This is an open source project, so we'd love to have contributors, and I'll maybe talk a little bit about that as well. So first, I'm going to talk about what is model-based systems engineering and kind of give a little bit of background around it, and then we'll jump into how to install the tool and go through a demonstration of how you'd model one of these systems. So in engineering today, I would say the status quo is we engineer with documents. So we write down our designs, we open Microsoft Word, write down all the things that the system needs to do, or Excel, and then for the next version, we update those documents. And there's always changes in engineering, so we're always going back and updating documents, and you end up with kind of these stacks and stacks of documents. So the focus up until recently has been on document management as an engineer. And no one likes that. No one wants a stack of documents to manage. And so model-based systems engineering is a way for us to do hopefully something a little bit better than document management. So this is from INCOC, and they define model-based systems engineering as the formalized application of modeling to support system requirements, design, analysis, verification, and validation activities, beginning in the conceptual design phase and continuing through development and later life cycle phase. And I'll talk what each of those things mean, but kind of the key to this is we're modeling a system, including all aspects of it, and ensuring that it meets the requirements we model. And we are using these abstraction levels to model the system to really understand what the system is. So I think really good engineering, and in this case, model-based systems engineering, is all about adding rigor. So as in the past, we went from manual drafting to computer-based CAD, that's about adding rigor to our engineering. And as engineers, we should continuously try to make the engineering field more rigorous so that we really ensure what we built is designed properly. So there's really these three components of rigor. I'm going to go through each one. One is having a standard language. The other one is using abstraction. And the third one is for automation. So in this case, for language, there's something called the systems modeling language, or SysML, and it's an open standard for systems modeling. And why a language is so important is because when you're talking to other engineers, it's really important that everyone's using the same words to describe the same thing. So if you call something a component, it would be very good for a common understanding of a system for that other person you're working with to have the same understanding of that component as you do. And that gets very hard if you're describing very complex behaviors and structures and requirements the system has, if you're not using kind of this standard language to describe things. So we use SysML to describe our requirements and architecture and design, the analysis and testing with precision. So when you say something behaves a certain way, that has a precise meaning for everyone to understand the same thing. The second thing is abstraction. And abstraction is really the key to engineering analysis. And if you're familiar with like science and mathematics, we use abstraction all the time. So in math, we use like models, like a model of a Fourier transform or some mathematical operation which doesn't match how things really behave exactly in real life, but they provide close approximations. And that's what abstraction is to remove certain details and get very close to describing how something is in order to improve understanding. So we want to select the aspects of an engineering design that are relevant to answer the questions for the stage of development. So if you're more at like the concept phase, you want to answer questions about what is this feature or system that we're developing and why would someone want to make use of it? Like what's their goal for this feature system? So that's like a specific question you have. And so you want to remove all the other details that aren't important to answering that question. And then as you go, you get into lower and lower details with more details added, and use abstraction for everyone to really understand the design. And a third important part is automation. And this is just like software engineering. We can use continuous integration to improve the efficiency how we develop software. And the same thing we can do for engineering in general, because automated systems have these highly repeatable effects. And so that means we can use automation to automatically validate that our designs are correct and consistent and of high quality without an engineer having to manually check things. And the example for, as an example with computer-aided CAD, you do like things like clearance checks and other checks of your design to make sure that, hey, all of your tolerances are how you design them. Well, if we're doing other types of engineering, you want similar checks to ensure your design is really right. So for abstraction, we actually are able to define certain abstraction levels, and these are the ones that I usually define. So you have a concept level, and this is where you define the problem you want to solve. You have a logical level, and this is where you create a solution agnostic to technical choices. So it's kind of free of how you're actually going to implement it. And then you have a technology level where you create a solution to the problem that you define using a specific set of technical choices. And finally, you implement the built artifact. So that would actually be the actual software that you implement, or that actual piece of hardware that came from the CAD model that you created that gets put onto, into production. So these are, if you standardize your abstraction levels so everyone has the same understanding of what belongs in each level and what questions you can answer in each level, then when you're making your design, you can focus on those key questions that you have at each of those stages and abstract away the details that aren't important. There's also 3 pillars of model-based systems engineering. There's behavior. So this is the functionality a system or feature must have. What must it do? So you're looking at the behavior it must have, how it transforms an input into the system into an output. That's the behavior. A structure is how your system or feature is actually constructed, how it's hooked up. Whether that's a hydraulic system where you have lines where your hydraulic fluids connect to different parts, or you have electrical structure with wires and computers and ECUs connected to each other. That's the actual connection of your system and how it fits together. And then the final pillar of model-based systems engineering is requirements. And so these are the constraints you put on the system based on that defined behavior and structure that you created. And those requirements should define what you want out of the system at each abstraction level, but you should try to avoid defining how it must be designed there, because that overly constrains the design from multiple implementations. And those requirements will get more and more detailed with more technical details and more constraints as the design goes down into the different abstraction levels. one of the key parts of model-based systems engineering is you can connect the behavior and structure and requirements all together. So you can model the behavior that the system must have, show how the structure that you define of the system satisfies that behavior, and then also connect both the behavior and structure to the constraints you put on the system in the requirements. So that was kind of some background about model-based systems engineering. Now I'd like to kind of jump into actually modeling something and show how a model-based systems engineering tool would work. In this case, we're going to use Gaphor, which is this open source UML and SysML tool that was implemented in Python. And as I said, 3 years ago, I learned Python to implement an open source modeling tool and got involved in Gaphor, which was a tool that already existed but hadn't been updated in a while. And we just released version 2.0, which adds support for SysML, for this systems modeling language. So if you want to download this, you can go to gaphor.org. That's probably the easiest thing. And there's download links right on the front page for all the different operating system, Windows and Mac OS. And also there's instructions how to install it using FlatHub, which is a cross-distribution installer for Linux. And so if you want to follow along, definitely go ahead and download one of the installers and install it. I'll also show you how, if you have the, I guess, right prerequisites installed, we could install it locally and launch it using pip. So this is also the GitHub page. So if you're interested in contributing to Gaphor, this is the page. And if you go down here and look at the installation instructions, I'm on Linux right now. So in order to make this run, I need to apt-get install these dependencies to allow me to run it. And if you're on Windows or Mac OS, there's slightly different dependencies as well. For example, for Mac OS, you need to use Homebrew and then install these two dependencies for GTK, which is the graphic toolkit we use. And Windows, you can also set up a development environment as well using this MSys2, which is a environment for Windows. So I already have those dependencies installed. So I'm going to go ahead and show you how you could pip install Gaphor. So I'm just going to create a new directory, and I am in Linux, but you could do something very similar in Windows or Mac OS. I'm going to just create a directory called Gaphor model, and then I'm going to change directory to it. And then I do have Python installed. And as you can see, it's the latest version, 3.8.3 at the time, I think the time of giving the talk right now. And I'm going to create a virtual environment. And so if you're not familiar with what a virtual environment is, it's kind of like an isolated area for you to install a Python application or library that will ensure that it has its own place to put the dependencies. So the issue you might run into is if you pip install stuff to your system Python, then if you have multiple apps or libraries that take different versions of libraries, then you might get conflicts in the different versions. So this kind of creates an isolated environment for that. And I highly recommend creating a virtual environment if you're going to develop in Python. So I'm typing Python-M, which stands for module, and VENV is the virtual env that's built into Python. So I'm telling Python to launch this virtual env module that's built into Python, and then I'm giving it a directory, and I'm telling it I want to go to venv as the directory we're putting the virtual environment in. Is there any questions from anyone so far? Okay, so it finished and created a virtual environment. So I'm going to go ahead and kind of put myself into the virtual environment called activate the virtual environment. And so I'm going to type source and go to the directory, this .venv, and the way to activate it is in a bin folder, and I type activate. So it's source.venv/bin/activate. It is a little bit different in Windows. The activate script is in the scripts folder instead of bin, but it's pretty much the same thing. And you can see here now it says .venv, and so that means our virtual environment's actually activated. We can also see that nothing is currently installed. So if you type pip freeze, pip is how you can install Python libraries and apps from PyPI, which is the area where pip gets all the libraries that are loaded on the internet that people can contribute to. So we want to just pip install Gaphor now. And now it's going to go automatically collect all the dependencies for it and install them all. So if this was your first time installing it, it might take a little bit longer because PyGeobject and PyCairo need to be built. So you might see a few more pieces of information, but it is pretty quick to install. And now we can see when we go to pip freeze that Gaphor is installed. It's version 2 with the dependencies needed for the app. So now we can go ahead and launch Gaphor by just typing Gaphor in. And it launched. You can see it went pretty fast. You also see this dialog that came up. It's telling us that Gaphor uses services and kind of has like a service-oriented architecture. So Gaphor, when it launched the application, is going off and kicking off all these services. So there's different ones there's an event manager, a tools menu, like a copy and paste functionality. The undo manager has its own service. So it's all built into separate services. So that's kind of the information it's giving you, that it kicked off all the services. So this is what Gaphor looks like launched. Kind of just our way around a little bit. This is all written in Python once again. And the toolkit for the graphical app is in GTK. So at the top, there's a selection. And by default, it'll say UML. That stands for the Unified Modeling Language. And that's normally used to model software. In this case, we're going to try to model like a system of some type. And so we'll use SysML that I talked about, was that model-based systems engineering language. In here is kind of a tree view, which shows everything that's in our model. And then we have a toolbar of things to add to the diagrams. And when I talked earlier about there being a standard language for SysML, all this nomenclature has a very specific, precise meaning. So when we use the different relationships, it has the same meaning to other people also modeling using SysML. And it is like an open standard. So you could be an engineer working for one company or doing something as a hobby and share your model with someone else, and they would have the same understanding at a different company what those symbols mean. So that's pretty powerful. So I guess we said we're going to build something. Does anyone have a favorite system they would like to build up? I guess probably something easy like an air compressor would be good, or a toaster or something like that. Does anyone have any favorite system they'd like to build? All right. So let's do an air compressor then. So what I did is right-clicked on this top package here, and I'm renaming our model to an air compressor. And then what's in this main area here is the diagram that we're going to model in. And when we saw those abstraction levels before, I'd recommend kind of breaking up your model into the abstraction levels. So when we model things, it's very clear which abstraction level we're working on. And then also we'll break it up by which pillar we're using, the behavior, structure, and requirements. So I'm going to right click again and create a new package. And I'm going to call this one concept level. And then we're going to create a new package again and call this one logical level. And finally, we're going to create one called technology level. So I also like to have in the main package here, like a model navigation. So we're going to go ahead and name this model navigation, and eventually we'll put kind of our most important links to our most important diagrams there. So in the concept model package, we're going to create, and sorry about kind of the boilerplate of setting stuff up, but we're going to create a few more packages. So we're going to create one for requirements, one for behavior, and one for structure. So now we have behavior, requirements, and structure at the concept level. And we can also add those to the logical and technology level. So one thing I like to do when we're creating a new system or feature, we're at this concept level where we want to really define what the problem is we're trying to solve. Often engineers love jumping down into all the details without taking, abstracting away all those details and thinking about what the problem is we're really trying to solve. And, what are the attributes our system or feature must have. So kind of starting at this top-down level is our plan. And normally I like to start with a behavior diagram. So we're going to go ahead and create a new diagram. I'm going to call it use cases. If you're familiar with other model-based systems engineering tools, most of them have a different diagram type for every type of diagram you're going to make. So if you're going to, like a use case diagram is a different diagram. In this app, all the diagrams are the same. And so you can really model anything you want on them, which I think can be pretty powerful, but just a little bit different if you're not used to it. So we're going to go ahead and just name the diagram what we're going to use it for. So a use case diagram defines the goals that a user of the system has for the system. So we're going to create an actor, which is kind of this role we have. And if you want to rename stuff, you notice you can either just double click and the pop-up comes. We also have this sidebar here where we can also rename things there. And some of the diagram items will have a lot more options to select from to customize what you're drawing. And you can hide that with that button there as well. So maybe we could call this person the operator. So we have an air compressor operator. And next we want to define a use case for that operator. And so remember, we're trying to define what the goal is for this operator using an air compressor. Anyone have any input on what the goal of someone using an air compressor is?
Make a lot of noise.
Yeah, annoy your neighbors. So maybe like, I think you normally use an air compressor to like store energy in pressurized air, something like that.
I never thought of it that way.
Okay. So you want to, you hook up your air compressor, you pressurize the air in the tank in it, right? And now you have kind of this energy you can make use in your tools or pumping up your bike tires or whatever it is, right? So then we're going to connect the operator to our use case. Sorry, did someone say something?
I wanted to ask, how long did it take you to abstract away that? Because I think that's a really great summarization, but I think it would take me a while to figure that out.
I have a little bit of practice creating use cases, but
have you done this one before?
I haven't done air compressors too much in, I guess, in use case diagrams. I have modeled air compressors before because some of the training materials for that. But yeah, I think just thinking about taking that step back on like, okay, well, what does that operator really want this thing for? And yeah, maybe some people would want it to create a bunch of noise or something like that, but I was just kind of trying to summarize what is that thing there for? Why did you buy an air compressor, right?
I think I'd say pressurized air, but I don't like long phrases for things. I think pressurized air is.
Yeah, so that'd be good too. And maybe you could say like, well, what's the goal of the user is maybe it's to pressurize air as well. That would be good. I was just trying to cover, that there's some energy there that you're creating that then you can use later. But I like just even pressurizing air is good. I think that does ask, okay, well, why do you want to pressurize air a little bit for me? But
I mean, the storage of energy is innate in that process. So I'm not sure what you're getting at by saying you're storing energy.
Yep, that's good. So we're going to also create a new diagram under structure and start defining what the structure of it is. So we've created this use case diagram. And the reason I'm going to do that is because I'm also going to show that this use case is kind of inside the air compressor. So if we create a new diagram here, and we could call this like the air compressor hierarchy or context hierarchy or something. So we have this structure diagram, and remember the structure is what defines how things are actually related to each other or connected to each other. And inside this structure diagram, we can use what's called a block. And so this is the actual like structural element that defines what things are. And in our block, we could create an air compressor block and say, well, this air compressor actually exists as this structural thing that we're making use of. When we go back to our use case diagram, we could then make use of that block and put it on there and say that our use case is part of this air compressor. So this is kind of like the use case of the air compressor is to store the energy.
So you made the object and you just clicked and dragged it over? I think I missed.
Yeah, so once something, this is not just like a picture drawing tool. It may kind of look like that we're drawing pretty pictures, but it actually has a data model underneath. So when you create an element in here, it connects that element in this data model that it's storing. And so that means you can reuse things. So I just dragged the block out of the structure here and put it on the diagram, and you notice I can create another one on the diagram as well. So you can reuse the same elements multiple times, and they have the model knows that this block is the exact same thing as this block. They're not just like pictures of it's not a picture we drew. It's like these are actually represent the exact same thing in the model.
And then maybe you'll get to it, but you'll show the power of like now somewhere you can find the use cases within air compressor of it or something like that. I don't know if that's
so we'll try to get to connecting like our structure and behavior and requirements all together. And if I don't quite hit on that, then please remind me, and we'll try to demonstrate that at least a little bit.
Yeah, no, that's the power of it. I take your word for it. I just want to see the power of it. I think that's the key.
So we've created this use case diagram. If there's no other questions about that for now, we can also finish creating our kind of structural diagram at this, remember we're at this concept level. So we want to put the air compressor in context of everything else that'll be around it. So I'm going to create a block and call it air compressor context, because we're going to show what kind of the air compressor is operating around. And you can see these blue lines that show up. That means it's aligning these blocks to each other. And so then we'd say, hey, what operates around an air compressor? So we already said there was that actor called an operator. So we can go ahead and create a block called an operator. There's also probably some like air tool we're making use of. Because otherwise, why have an air compressor if you're not going to do something with air compressor? And then maybe the other thing around it is atmosphere or air that you're going to compress. So then we can put relationships between them. And there's this thing called this composite association. And when you click on it, then you can create these relationships. So you start from the lower block and then go up to the one above. And this relationship means that this air compressor context contains an operator. So that's what that relationship means, that it contains it or is part of it. So we can continue making those relationships. There's also keyboard shortcuts. So in this case, I can hit Shift-Z and also create this relationship as well. And you can also, I guess, change the settings so you can use the same tool over and over again without clicking on the toolbar, but we'll just go ahead and click on it a few more times. So this is kind of that structural view at this really high level, once again, of, hey, what is around our air compressor? And we're saying the context of our air compressor contains an operator, the air compressor, air tool, and the atmosphere. So that's like a very high level structural view of the air compressor at that concept level. Is there any questions about that so far? Okay, so let's go down to like more of like a logical level. And remember for that one, now we are trying to create a implementation or technology independent solution for our design. Where in the concept level, we were trying to more like define what the problem was. So we're going to create our 3 packages again: structure, requirements, and behavior. And maybe we'll start with structure again. So now at like this logical level, we need to define what structure would make up an air compressor. So we're going to use blocks again in this. I meant to create a new diagram in the structure package. And we'll say this is the air compressor, like maybe like system hierarchy or something. And so we're gonna now create these blocks. And now at this logical level, we also have an air compressor. And we want to define what the air compressor is made up of, kind of independent of how we implement it. So one thing that might be in an air compressor is you probably need a tank to hold the air. So we'll add that. You probably need a motor. And I think any air compressor would need some type of pump to actually pressurize the air based on the work the motor does. And then you probably also need some type of controller to actually turn on and off the air compressor and control the motor. So I think that's how I would define, like, well, independent of how I actually implement, what type of pump it is, what type of motor, you know, is it DC or AC, how big's my tank, all that type of stuff. I'm just saying, like, well, any kind of, at this logical level, any air compressor is going to have these 4 things.
What about a valve? Is that him?
Yeah, I mean, that's maybe another thing you would say, like, well, hey, maybe an air compressor doesn't really do anything unless you have like some type of like shut off valve or something. I mean, I guess you could have one without one, but then your air automatically escapes, right?
Yeah, it's called a pump.
So you better have your tool hooked up right away, I guess. So you have your tank, a motor, pump, and remember we're saying with this relationship that the air compressor contains these things and our shutoff valve. So I like that idea, Charles, of adding a shutoff valve. And so now we've defined the structure at this logical level of what this air compressor does. I guess we could also maybe quickly talk about behavior and structure, or behavior and requirements as well. So let's create a behavior diagram. And let's call this like functional behavior. And there's a few different behavior diagrams. We already saw the use case in action and the concept level. There's also a few other ones. One's called an activity diagram, and it's very good at showing behavior from one area to another in the system. And there's other ones like sequence diagrams, which are good for showing the order of operations, and also state machines. There's a lot of states in your system. But we're going to focus on this activity diagram, which shows kind of the function of it, as we have the motor and the motor controller and the pump and the tank and everything kind of doing stuff for us, and what that behavior looks like. Remember, the behavior is transformation of like our inputs to our outputs. And in this case, our input is low pressure air and our output is high pressure air. And so then we want to show the behavior between them. So in an activity diagram, we show that by using these actions or activities here. And so maybe we'll start out and saying, hey, we need a behavior. And normally we would want like those to start with a verb. So what is the thing going to do? And we'll say, hey, our pump is going to pump air. And so that's the behavior the pump's going to have. And then in addition to that, we need our tank to store air. And we also have a motor, and I guess it's going to generate torque to pump the air. And we probably need a motor controller, and it needs to, I guess, control the motor and what type of motor you have. And this is supposed to be kind of independent of the actual type. And then maybe we need some type of sensor probably to sense the pressure in the tank, because you probably don't want to just keep on pumping and pumping, or otherwise you need some type of probably relief valve or something, right? But normally you'd want to pump up the pressure to some like high point and then stop pumping, and then when the pressure goes down below a certain level, then you start pumping again, right?
Dan, a quick question.
Yep.
When you're in the activity diagram, I noticed that the icon shapes are rounded, which must mean actions. Is that automatic because you're in that?
So it's because I was using this actions toolbar. So I was using an action when I drew, and that round shape has specific meaning in SysML. So that's one of those language things where then everyone looking at a diagram with these rounded shapes knows that's an action and not some structure thing or some other element. Hopefully that was clear. So now I'm gonna, I guess, hook these up. So we want to generate torque to pump the air. We want to pump the air to store it. We want our motor control to, I guess, generate torque in the motor, and our pressure sensor to go into the motor controller. And I guess our air storage needs to come back to our pressure sensing there. And I'm not going to spend too much time making this look pretty, but you could kind of, you could square off all your things there. And then we're going to say, hey, out of this, we're going to have high pressure air. And the input, we said we're going to have low pressure air, right? And then we're going to hook up our low pressure air into our pump. And our storing air ends up becoming high pressure air. And we'll also add one more thing. This is like an initial node, and it tells us that this activity diagram is starting somewhere. And so we'll hook that into this control motor here. And then I guess if you turned off the air compressor, then that would also end the activity. So we'll put like a node here, designating this as the final node. So if you turn on and off the motor controller, that's how you'd exit the activity as well. So we could clean this up and square off all the corners. It's also very common to add swim lanes in these diagrams to show like, hey, this is the motor controller doing this. This is the motor, the pump, the tank, and kind of divide stuff into partitions. But I'll skip that for now, just to keep this simple. Are there any questions about like a behavior diagram? And notice we kind of used abstraction to abstract away details of how our actual designed air compressor will actually work. We have defined how any air compressor would work, right? And independent of the technology we used, independent of the actual motor we picked, all that type of stuff. So we're coming up to the top of the hour. Maybe we could talk a little bit about requirements, because we haven't talked about that yet. So we could say like, these are now functional requirements. And you might, oh, I didn't want to create a package. Let's create a diagram is what I meant to do. Now you could also have requirements at the concept level. And remember, that would be stuff that's more defined on what the problem is. So you might have like a marketing department saying, hey, I'm the air compressor marketing department, and our customer wants, this, I don't know how you measure tanks, but such and such a size tank, right? And that's what our ideal air compressor tank size is, and therefore that's what we want you to build. So that would be actually an attribute. Maybe it's like an 8-gallon tank, right? So you could have a requirement up at this concept level, and we could write that. And we could have like an attribute requirement up here, right? An attribute. And so marketing comes to you and says, hey, we talked to all of our customers, and they want a air compressor that holds 8 gallons. So then you could create a requirement for storage capacity. And so the requirement has an ID and text, but you could say in the text, this is actual requirement text, and you could say air compressor shall have a minimum storage capacity of 8 gallons. Right? And so we now have a requirement that says, we know at this attribute level how big our tank must be, and then we'll take that into account as we're designing our air compressor. And you could also have like a hierarchy of requirements. So this could be one, and then you could have other requirements derived from it that also put constraints on the air compressor. And you could have other requirements on, it's sold in the US market, so therefore it has to have 120-volt power hookup, or, whatever the attributes are for the air compressor for how you're designing it. So then we could also put functional requirements in. And I think that functional requirements are best derived from the actual behavior that we created. So then you could put requirements on, hey, how the motor controller must work, right? So I think we said, hey, our activity starts, remember, at this motor controller, and it starts there and ends there. And so I think there's like some behavior there that we want to allow the customer to turn on and off the motor controller itself, right? So we could create a requirement at this functional level and say, well, there needs to be an on-off switch. Say the motor controller shall have a on-off switch, like that, right? And so that'd be a requirement that's derived from your functional behavior, and we could also derive more requirements, that we're putting constraints on the system. So we can say the motor torque must, or the motor must provide torque to pump to the pump to pump air or something like that, right? So that'd be a functional requirement relating the motor and its generation of torque to the actual pump itself. Or the pump must pressurize the air and store it in the tank.
Dan?
Yep.
Are safety requirements overarching, or are they at the level of functional requirements, or?
Yeah, so I guess for my work, I actually do functional safety a lot. So that's looking at what hazards could exist in a system and designing the system so that, the systems don't cause hazards for the customer or cause harm to the customer. So we would actually go back to this very high level use cases and say, okay, well, what is this system supposed to do? And then we would define, hey, it's supposed to store energy in pressurized air. Okay, well, how would that malfunction? Well, we could, I guess, unintentionally pressurize the air. We could fail to pressurize the air. We could pressurize the air too late, kind of go through all those different scenarios of malfunction. And then we do a hazard analysis, which is a technique where you'd go through and look at, you kind of rate the risk for each of those malfunctions to occur. Because some of those things, like would failing to pressurize the air cause a hazard? Probably not. But maybe if you over pressurize the air and cause the tank to rupture, that would cause a hazard for the operator. So then you could kind of create functional requirements based on that hazard analysis. And you could add those as well, normally to like the logical level. And so we just said about over pressurizing. So I guess you could do that a few different ways, right? You could add a kind of fail safe that a relief that lifts if the pressure gets too high, or you could really design the sensor and the controller so that it never fails and continues to pumping the motor when pressure is too high, right? So those are like a couple different designs that you could design in, but you could definitely add requirements at this functional level. So
I think the key that you identified was that the functional requirements come from the hazard analysis. That I think is, so thanks for that.
Yep, exactly. So that would actually cause us to add maybe to our functional behavior and our requirements that maybe we need a pressure relief valve because we decided we couldn't ensure that the sensor could never fail or that the motor controller could never pump when the pressure is too high, right? So that you could design it like that as well, but that might be more challenging to try to create a system that can't fail in those ways. But you could just add a safety mechanism backup, a pressure relief valve. So then you could just create a requirement that the air compressor shall have a pressure relief valve. Okay. So those are requirements, and you'd actually create like a hierarchy of these requirements as well. So you could derive these functional requirements from the attribute requirements we talked about. So we had a requirement for storage capacity, if you remember. So maybe now at the functional level, we'd have a lower level requirement that would more precisely define what the actual capacity is, or what the tank shape must look like to get that storage capacity or something like that. So we'd have kind of like this tree of requirements we develop. I know we are probably just about out of time. I guess the main things I wanted to show was kind of showing also how to connect stuff. And so maybe one other thing we could show, we had structure at this logical level. We had a requirement for functional requirements for a pressure relief valve. So maybe in our air compressor here, we need to now add a pressure relief valve. We have a pressure relief valve, and we've added it in now that we've done like a safety analysis. And then when we have our requirement and go back to our functional requirements, we can actually take our pressure relief valve and bring it in here. And then we can say that this pressure relief valve satisfies the requirement. So now we've actually put a relationship between the structure and requirements. And we can do a similar thing. I mentioned the swim lanes earlier for an activity diagram. If we had swim lanes and partitions in there, we could actually allocate the behavior to the blocks. And we talked about connecting the blocks to the requirements, or the structure to the requirements. So you can see you can kind of quickly build up this model where you can connect the behavior and structure and requirements all together, and really have this design that's made from those three different kind of legs of a stool. Really ensure that you have a really rigorous design, kind of top down. And after this, then we were starting to get an actual like technology level implementation. So we would define, hey, what type of motor must we have to meet the other requirements, and all the other low technology stuff. What type of pump must it be, and what kind of piston rings must it have, and all those types of things. So we would get then now into that kind of lower level. Is there any questions?
So when we're done with the pictures, does this turn into other, like a Word format of, hey, I just want to print off the requirements, and I don't want it to be in Gaphor. I just want to have a list of requirements and the things that satisfy those requirements to prove to my boss that, yeah, I looked at all these requirements, and this is why I think I'm good.
So right now in Gaphor, we can export to PDF and then to image formats, PNG and SVG, and also like XMI, which is an XML model interchange format. It doesn't yet support like auto-generating like a report, like a Word document, but that is normally possible in some of like the enterprise like tools, but we don't have support for that yet. But you can kind of export maybe your own like PDFs and put together a report based on it, or pictures. Yeah. So, yep.
But I guess this just explains to me that, yeah, I can make things in different parts of it, like the structure, and I just drag in the component to the other diagram to show, to form the relationship.
Yep, exactly. Yep. Thanks, Xander, for that. Any other questions from anyone?
Have you seen, Dan, a very complex system built with something like this?
Yeah, so at Ford, we use this to build very, very, very complex systems. And it's also heavily used in aerospace, defense, and biomedical. So I would say probably most of the extremely complex systems that are being built now are often using an approach like this. I guess I found, working on, say, a new F-150 has a 10-speed transmission, and the amount of complexity, the number of different gear state combinations that the clutches can put on or take off is impossible for one engineer to even wrap their head around how complex it is. And it has multiple computers controlling it all. So definitely using techniques like this to really in detail, rigorously understand the design of the system. And then you can have a bunch of people all working in the same model, so everyone's understanding is the same. And that often, especially for large organizations, that can be a big problem that, one engineer thinks they understand how the system works, another one thinks they know as well, but there could be often disconnects in one engineer is making an assumption about something and another one has a different assumption. So being able to share a model and work on it as a team is pretty powerful. But definitely, Boeing uses this for the aircraft design, Lockheed Martin, the automotive industry uses it. It's in pretty prevalent use.
And then kind of dovetailing off of that, are there any features to share models, or is it just save the model and put it to a shared drive, and then on the other end, like sending this, like, I guess I kind of already asked it, but like sending the list of requirements to a coder of if you got to the technology or logical level, and is there any support for that, or just as you see it as how you'd work on it?
So the file format that Gaphor uses is XML. So you could definitely put the model in version control, like for example in Git, and then put it in a repository that multiple users share. It would be a little challenging because you would have to, I guess, as you're merging changes back in, and if there's conflicts where two people maybe made edits to the same diagram, it'd be a little bit challenging to merge them because you'd have to be kind of trying to read through the XML to figure out what changed. I definitely could see it would be awesome in the future if you could also do like a visual diff, or visually could see, hey, you have a screen that comes up and it shows, hey, this was the old version that's in the master branch, and here's the new version, and show the differences visually. Something like that would be probably not that hard to implement. It would be really powerful. But that, kind of that version control system like we use for software could definitely be used. And then there is this XML model interchange format so that other people maybe using different modeling tools might be able to make use of the model. One thing that's really powerful about this is there is this data model underneath all this. This isn't just pictures. So it'd be definitely possible where you could connect the data between Gaphor and other tools. And there's something called OSLC, which is a open standard for connecting data, especially like requirements data, and it uses kind of web-based technologies to connect data between tools. You could use something like that. Or I guess, create other integrations or APIs to connect data between your tools. Like if you wanted to view your requirements in a requirements tool, or view them on a web page, or make use of data from your model. This is like a descriptive model because we've described what the system does. You might also want to connect it to maybe like an analytical model to do analysis and benchmarking and make trade-off studies and stuff like that. So definitely with this comes power to start connecting like engineering data together, and make use of that engineering data throughout the design, because not everyone would be doing this type of design. Some people might be designing software or doing CAD work or all kinds of other activities, right?
Yeah, no, I'm just thinking like to prove that you did it, either like, oh yeah, this software version contains I'm thinking software, but this software version contains the fulfillment of the requirement, or I guess the other idea is writing your requirements in a test way of saying, if I input this, then this is the output. As a way to, I forget what that's called, where every time you compile, you run tests on it, but to try to set up that environment where your code is always being proven out, or just to always have those point of proofs.
Yep. Yeah, so that'd be like on the like continuous testing type of approach. You could definitely, so we talked about technology level. Maybe for a motor controller, we'd have technology level requirements, how the controller works. And then you could even derive software requirements from those. And then you'd probably want to connect your software requirements to your unit tests themselves. And as you said, then you could continuously test your software meets the requirements. So you could definitely do something like that. Any other questions? Okay, thanks everyone. I really appreciate it. Go ahead and stop sharing.